Good afternoon or good evening, everyone, wherever you are. So
Good
just
evening.
have
Good evening.
1 minute to start the session, and maybe just to make sure that we have the 3 presenters. And I would just like to reminder that I will be co-chairing this session with Dr. Badr Hamoud Al-Rashdi. So basically we have 3 presentations. I don't know if all the presenters are available here or
Doctor, as showing is all is here.
yes, I can see some of the names. I think they are connected. Okay, so I think it's now time, so we can start with the first presentation. So Ashi Kansal is he around? I can see his name here. Can you unmute
Yes, sir.
your?
So I'm the co-author Satish Akkad, who will be presenting the.
Oh, okay, so you will be presenting, not the Ashi Kansal.
Yeah, she has some
Okay.
technical problem at her end, so I'll be presenting on her behalf.
Okay, I didn't have this information. Anyway, so just you have 15 minutes to present your paper. And
Sure.
before you start, of course, just give very brief introduction of yourself.
Sure, we'll do the same.
Okay. And I will just remind you before the time is ending, I will just remind you maybe 2 or 3 minutes before the time is ending. Okay?
Okay, no problem, no problem.
Okay. The
So
floor is yours.
is my
You can
screen
share your
visible?
screen. Yes, we can see your
And
screen.
am I audible? Yes. So basically, so I am Satish Akkad and my co-host Ashi Kansal. We both are from India, and currently we are pursuing our PhD researches in IIT, Indian Institute of Technology, Kharagpur and Roorkee, respectively. So after this was a short brief about myself and my co-author. So in terms of paper, the paper is cost-benefit analysis of double skin facade over single skin facade in warm and humid climate. So I'll be starting the presentation. I think is it visible to all?
Yes.
So in the present
Yes,
scenario in India, there is a large amount of electricity demand which is pertaining over there, and the carbon dioxide emissions are also very strong. And most of the carbon dioxide emissions are from due to coal. So for energy production, as the coal shortage is also in many countries and the coal is being used, so this is the problem which is being pertaining in the country. So the energy consumption in building is 35%, and it is growing at a 8% annual growth rate. And in the commercial sector is the one which is maximum at the growth rate right now because of being a developing nation. So commercial buildings have the potential to save about 40 to 50% of energy. And in that 50% of energy, HVAC accounts for 52% of the total load. To reduce this HVAC load or to reduce this energy demand, we can do many things that can be done for various factors and climatic conditions and all, out of which 26% is due to the building envelope, which can be controlled. So for controlling this building envelope part, we require a high thermal lag of uh, walling material and things over there. So in ancient period, we used to have large wall size section and everything. So to overcome that, people have started to come with various new kind of technology, techniques and materials and all. So DSF is a kind of, that is double skin facade, is a kind of a technique which reduce environmental impact and operational energy demand in the building. It also facilitates the buildings with ventilation, glare control, daylighting, better acoustics and aesthetics. So in India, the warm and humid climate, which the name suggests is warm in nature and humid, covers over a large part of the country. And we need to control high humidity, high temperature. So basically, we need strong ventilation and high thermal lag to stop the heat from entering in both the covering both the cases. So DSF comes out to be a very, very good technique as it facilitates the ventilation and thermal lag both. So the concern was that there can be an increase in initial cost of DS double skin facade over single skin facade, as a new layer has to be added onto the building and all. So we had to calculate is this double skin is feasible or not in terms of economics and energy savings. So basically, a double skin facade is an exterior interior skin which is separated by ventilated air cavity, and this cavity is considered as a buffer zone, and the temperature difference between the cavity helps the natural ventilation circulation to go on, as it warms up the air which moves out, and the cycle goes on. So in many cases, by researchers, by many authors, it has seen that it can result up to 50% of reduction, but it changes from place to place, climate to climate, and material to material that we are using. So we took a case example of Krishi Bhavan building, which is constructed in Bhubaneswar, which is in Odisha, India, and the double skin facade has been employed over that building, and we took out the results through various softwares and found out is it actually working or not. So for that, in the design builder software of Energy Plus, we went for designing two type of buildings, which one containing a double skin facade that is shown on the left, while on a building which contains a single skin facade only, with all the other things similar in each other. So basically, we saw that there is a variable energy reduction consumption all over the year, which ranges to 4.7% in November to 13.4% in June. That is, when the sun is at its max at peak, we can see more amount of energy reduction present over there. So it was seen that an annual energy reduction was up to 7% of the total energy reductions. So first thing was to do the cooling load calculation. So for the cooling load calculation, we went for a sensible load calculation, which was see that it is changing from 5.5% to second floor to 10% first floor. So we can see as the buffers are increasing above, the energy consumption is decreasing. So that can be said like in double skin facade, due to that air buffer will act helpful for our case. So it gave that us that insight. So we need to reduce the latent cooling load for the building. In terms of light consumption, due to an extra facade which has been developed, there will be more darkness in the light, because light has to now cover from two layers, which can be in form of jali or opening or something. So we have to see that how much lighting energy or electricity demand for lighting is to increase is being increased. So it was seen that there was an annual increase of 34.4%. So now we had to now we got the things that how much cooling load and energy demand has been reduced. Cooling load has been reduced. How much lighting energy demand has increased. So now we see that if the cooling load is reduced, then we can remove some parts from air conditioning that had air conditioning prior. So basically, we saw that how much cost saving due to if HVAC systems will be removed from some parts. So we through the Central Public Work Department in India, they have some kind, they have specification costing for everything, for every system and kind of material and all. So for VRS system, we saw per horsepower 55,000 of Indian rupees can be saved. We calculated the whole horsepowers that are required, and we are about 90 lakh 24,000 rupees that was saved, and this was a one-time cost that was being saved. In terms of energy, because this firstly the system is not employed, and when the system will not be employed, then that system will not consume energy. So we saw that there was an annual energy decrease of 3 lakh 21,000, and which sum up to 18 lakh 30,000 of Indian rupees. And this will be a recurring cost which should be taking place annually. So then we went for cost expenditure due to lighting system, because now the more number of lighting will be for a longer hour, the lighting will be switched on and all. So the more amount of energy will be consumed in that. So we calculated through daylighting analysis that 1 lakh 34,000 of Indian rupees will be invested every year for paying those electricity bills as a recurring cost. So there are some drawbacks and some advantages that we have seen over it, but we have to see that overall it will be feasible or not. So cost of construction of double skin facade over single skin facade, because in single skin facade, the extra walling that has been created in our case needs to be compensated with the benefits it is providing. So with the analysis of rate and the unit rates that we get for the area, it was calculated that the total cost of construction, which was increasing, was by 96 lakhs of Indian rupees, and this was a one-time cost. And over from the single glass units which were used for windows and all, now double glass units were being used. So the total cost that was again invested initially was about a 22 lakhs of Indian rupees, which was again a one-time cost. Now to as we have some extra units of double glass units, we have an extra walling, so we have to take care of their annual repair and maintenance, because that's an extra cost that we have to pay for them. So according to the maintenance and all, a total amount of 1,35,000 was for operation and maintenance of VRF system, which was saved. Extra brickwork which was done for the double skin facade, so an extra 1,44,000 has to be paid annually as a recurring cost. And as the single glass units were replaced by double glass units, so an extra of 33,000 Indian rupees will have to be paid as an extra recurring cost for the operation and maintenance of that structure. So total expenditure and saving that we went through. So basically, if I putting all these things in a nutshell, so the cost of construction of double skin facade over single skin facade was 96 lakhs one-time cost. Cost of construction of DG over SG was 22 lakhs. These were one-time costs that were paid at the initially construction of the building. Now comes the recurring some that we have to be paid. So extra light that we are consuming is an extra electricity bill we have to pay annually. Extra operation and maintenance of the extra brickwork for done for double skin facade, and extra for DG over SGUs. So extra for that maintenance came out to be 1,44,000 and 33,000 respectively annually. Now there will be some kind of savings that have done. So as I've told you, the HVAC system which was being deployed over there, the part was some part from some areas it was removed. So 90 lakh was the initial amount that was saved, which is a one-time cost which was saved at the start of the construction. The cost saving due to less energy consumption was about 18 lakhs, which will be recurring cost. So it is a kind of a recurring savings that is present over there. And in operation and maintenance of those VRV and VRS system which we had to pay earlier, now with the double skin facade, that amount of 1,35,000 is not to be paid now. So for the returns that we are getting, we have to first calculate a payback period. So it is the amount taken to recover the investment cost, or the time taken by the investor to reach the break even. So I have employed an extra X cost on a building, and I am placing some of the facilities for in that building. So are these facilities able to compensate for that X cost or not? Can be told as the payback period. So a discount rate was present in India is about 7%. So payback period was calculated, and it came out to be that in 1 year and 10 months, the extra amount that has been paid on the double skin facade over single skin facade could be easily retracted back, with considering all the inflations and everything into account, because the discount rate basically takes that into account. So other thing was cost benefit ratio. Cost benefit ratio helps us to see that the present worth of the benefit, that is you are investing, is is above the present worth of the cost that you have invested over it. So we have seen that in the whole chart, it can be easily seen that the CBR ratio is always greater than 1, which shows us to be a very profitable relation, and it is gradually increasing throughout the years. And the return on investment, that is the compare the efficiency of different investment that we have employed on it and are getting returned or not. So the rate investment of DSF was 29 lakhs 19,402. The profit earned per year is 16 lakh 54,000. Profit earned is in terms of less amount of money being invested, less amount of electricity being consumed. And in the conclusion, at the end, I would I would like to share all the things in a nutshell, that TSF is a successful design intervention over SSF, but it is a successful for warm and humid climate for which the study was being conducted. But it can be seen that DSF varies from in lot of many perspectives. So it varies in terms of type of material, type of gap between the two skins, what are the external environment conditions, what are the materials being used and techniques being used. And it can be clubbed with various other techniques, like we have cool roofs, and DSF can be clubbed to reduce the energy consumption of the building. So these were the references that were being followed all over the paper, and thank you.
Thank you so much, Dr. Hacker, for your nice presentation. I would like just to remind the audience that you can post your questions in the chat sections. And of course, the session for the question and answer will be at the end of this session, of course. Now we can move to the second presenter, I think Dr. Nikita.
Yes, sir. I'll just start sharing my screen.
Okay, thank you. You have 15 minutes, and if you exceed the time, of course, I will stop you, please. So please stick on 15 minutes
Yes,
time
sir.
for your presentation.
Yeah, sure, sir.
Okay, thank you. Yes, it's fine. We can see your presentation. So go ahead, please. Dr. Nikita, we cannot hear you.
Hello, am I audible now?
Yes, now we can hear you.
Okay, I'll
Thank you.
just begin. Greeting of the day to all. I would like to thank the organizers of the conference for giving us this platform to share our work. Before I start, I'll introduce myself and my co-authors. I'm Nikita Khatri, an architect and a postgraduate in building energy performance from CEPT University, India. Rashmin Damle is an assistant professor in building energy performance program at CEPT University, and Rajan Rawal is a senior advisor at the Center for Advanced Research in Building Science and Energy, CABS, and a CRD professor at CEPT University. Today, as a presenter for the session 5, that is Construction Materials and Climate Change, I'll be presenting my research work titled Hydrothermal Performance of Lime and Cement Plaster. It is an experimental and measurement-based study. The presentation time to 15 minutes will flow as per the following contents, where I'll be discussing introduction, purpose of the study, literature review, research methodology, results, and finally conclusion. To begin with, I would like to depict a larger scenario where the building sector in India accounts for 35% of the total energy use and growing at a rate of 8% annually. With the increase in population and urbanization, it is leading to increase in the need for future developments, and demand for space cooling is also rising, which is altogether resulting in a global concern, that is climate change. Therefore, it's time for us to make a conscious decision to make these development energy efficient, low carbon footprint, and sustainable. These have become significant area of research to reduce the environmental impact on buildings. The energy requirement of a building is directly related to the thermophysical properties of the building. A building envelope acts as an interface between the outdoor and the indoor environment. Across a building envelope, just as heat transfers by the virtue of temperature difference, similarly moisture due to the gradient of vapor pressure and relative humidity. This coupled effect is known as hydrothermal performance and takes place due to the hygroscopic property of the material. Amongst the various plasters which are available, like gypsum, cement, clay, mud, lime, stucco, cement is most commonly used instead of traditionally employed lime. Although advent of cement was revolutionary, but it is raising environmental concerns due to CO2 emissions, non-porosity, deterioration to buildings. And so to address these concerns, lime is reviving as sustainable material because of its breathability, durability, self-healing properties, and comfortable environment. With this context, the purpose of the study was to evaluate hydrothermal performance of lime and cement plaster by developing two test cells having similar geometry and construction. The objectives were as follows: to identify hydrothermal performance of the two plasters, human comfort, and compare the measured and the predicted data. To arrive at the methodology, literature review was carried out to understand as to how lime in recent research, where it discusses the moisture buffering capacity, inactivates virus and how it proves to be thermally optimal. Amongst the various models used for simulation, EMPD model, that is effective moisture penetration depth model, how it uses basic input of sorption isotherm and to understand the hydrothermal performance of plasters as to what geometry of experimental setup has been used in the studies. To proceed with the development of test cells, it was validated using the last point where it uses a wall surface of 1 meter square. The research methodology of the study was segmented into two parts, where the first part was to evaluate hydrothermal performance by observational data and development of test cells and measurements, and simulation-based study where the measured and the predicted data were compared. The test cells were developed as per the following construction, as we can see, where the volume was 1 meter cube, the plaster thickness was 15 mm with a mix of 1:4 as derived from Indian standards. During the construction, lime test cell had lime as the mortar, and similarly, cement test cell had cement as the mortar. The kit of parts of the test cell can be seen here, where a brick bed was laid. The top and the bottom surfaces were covered with impermeable sheet, and 4 vents on each side with an exhaust on top was to allow the air movement. All the air gaps between the various materials were covered with barrier foam. As we are discussing construction material in extreme climate, location of the test cells was Jodhpur, India. The city experiences a hot and dry climate where the temperatures range between 45 to 50 degrees Celsius in the months of May to July. And lime has been a vernacular material employed for plastering in the older settlements of the city and is believed to keep the indoor environment cool. With a tint of indigo added to the lime plaster, it imparts a blue color to it and hence known as the Blue City. The test cells are developed at my residence terrace, and this is how they have turned out to. This is cement plaster and this is lime plaster itself. After the development of the test cells, to evaluate the performance, 5 variables were identified along with the instruments, position, and type of measurement. The position of instruments in the test cells can be seen as follows, where the surface temperature was measured inside and outside at the center of the wall. Indoor air temperature, relative humidity, and glow temperature in the center of the cell. Outside air temperature and relative to in the outdoor environment, and moisture content and surface relative humidity on the wall surface on each side of the cell. All the identified instruments were installed as per the protocols. Surface temperature and moisture content were measured at the center of the wall surface, and all other thermal environment were put on a covered stone slab. To draw a comparison between the two, all the measurement protocols like distance, height were kept same for both the test cells. As a part of the results and discussion, I'll be discussing about the air temperature, relative humidity, human comfort, moisture content, surface temperature, and simulation. To begin with indoor air temperature, as we can see in the graph, this is a representation of 1 week of March, where it can be observed that for similar outdoor conditions, the indoor air temperature in lime is 3.1 degrees Celsius lesser than the cement. The significant difference was observed in the later half of the day. And as the lime plaster tends to resist the heat loss, which could be attributed to the wall assemblies, the cement test cell has a higher U value than the lime. And for the period of analysis from 1st February to 15th of April, the indoor air temperature in lime test cell was an average of 3.1 to 5.2 degrees Celsius lesser than cement test cell. As we move forward to understand relative humidity, the mean RH for both the test cells was lower than the outdoors. The RH in lime test cell ranged from 23 to 57%, where the range in lime cement was 21 to 61%. The difference of mean RH in lime test cell was 2.9% lower than the cement test cell. This was further divided into 3 categories as per optimum RH levels of 30 to 60%, and drier conditions of lesser than 30%, and humid conditions of greater than 60%. High levels of RH can result in mold formation, dampness on walls, whereas lower levels can result in skin dryness, chapping, etc. And due to the application of lime, it was noticed that due to hygroscopic nature of lime, it moderated the RH levels by adsorption and desorption. And for 8.8% of the time, indoor RH levels were better in lime as compared to cement. Temperature and humidity are the two measurable factors to define human comfort. The indoor air temperature range of 22 to 30 degrees Celsius and RH in the range of 30 to 60% was derived from IMAC and ASHRAE, respectively. And these were overlaid on both the plasters, which divides the whole segment into 9. The period of analysis started from February, which is the winter month, and hence more number of cold points were observed in the optimum RH levels. Excuse me. And only 0.2% were in cold and humid segment. Further, as we can see, for 46% of the time, lime tessel had comfortable environment as compared to cement. As the days passed, month of March approached and mid-April, the temperature rose till 43 degrees and hence number of data set points were more in hot and dry segment. The temperature alignment of lime plaster and cement plaster can be observed in the range of 11 to 40 degrees, whereas for cement, it was from 16 to 45 degrees. Similar behavior was observed in moisture content of the walls. As we can see in the graph, the indoor RH fluctuated and moisture content also showed the similar variation. With measurement of moisture content, it was observed that lime plaster had a stable fluctuation as compared to cement plaster. And in February, as this is a representation of 2 weeks, or 1 of February, 1 of March, we can see that the east wall surface of cement plaster shows a higher moisture content of 1.8, whereas lime was still stable to 0.7, with an average moisture content in February for cement was 1.5, and for lime it was 0.6, whereas in March it was 0.9 and 0.5 per lime. This is indicating to the hygroscopic property of lime. Moving ahead to understand surface temperature on the east wall surface. To understand the thermal behavior, surface temperature was analyzed, and this is a representation of 1 week of March. As per the sun movement, the temperature rose in early morning hours from 8 a.m. to 11 a.m. And during this interval, the average temperature in lime plaster itself was 2.1 degrees Celsius lower than the cement. Thermal lag was also observed of 1 hour, which means that the peak temperature reached 1 hour later than in lime as compared to cement. Similar nature was also observed for southern surface. The temperature was significant post 11 a.m. till 3 p.m. And during this interval, the average indoor temperature difference in lime plaster itself was 1.3 degrees Celsius lower than cement. A thermal lag of 1 hour was also observed here. Post-measurement segment, the test cells were to be simulated to evaluate the hygrothermal performance of both the plasters. And as a part of the methodology, the cells were modeled in Design Builder, input of variables which were close to the real case scenarios, and simulation of test cells. These were the input parameters which were taken forward.
Excuse me, you have 3 minutes left. You need to
yes, sir. I'm just
count for that time. Okay, thank you.
Yes.
Sorry.
And these were the input parameters which were fed into Design Builder. And as a result, and way forward, for both the test cells, the predicted and measured indoor temperature and RH were in good agreement. And they showed a variation of only 2 to 6%. Hence, this EMPD model could predict the hygrothermal behavior of the test cells. In view of the above discussions, lime as compared to cement shows a promising opportunity towards application of lime for following reasons: that it reduces the air temperature by 3.1 to 5.2 degrees Celsius, is 46% of the time more comfortable, moderates the indoor RH levels, shows stable fluctuation towards moisture, reduces the indoor air temperature, surface temperature by 2.1 degrees Celsius, and could predict the hygrothermal behavior of test cells. As a part of future recommendations for the study, to control the environment with fixed ACH in the cells, to run the EMPD model simulation with the sorption isotherm of the materials. And as also seen in literature review, that lime tends to absorb CO2, hence monitoring can establish it to conclude on the indoor air quality of the spaces, and scaling rules to identify how such small experimental setups can be used for actual building scenarios. Thank you.
Thank you, Dr. Nikita, for your nice presentation. Now we can move to the third and the last presentation. So by Professor Adrian.
Yes, thank you very much.
Professor Adrian. Thank you
I
so
hope
much.
you can see the screen. I will start the presentation.
Yes, we can see the screen now. So just move to the presenting mode.
Okay, thank you very much. My name is Adrian Pitts. I'm a professor of sustainable architecture at the University of Huddersfield. I've been researching in the area of comfort now, I suppose really for almost all my career, which is more than 30 years. But of that time, I've had the pleasure of working with many people from different parts of the world and in different types of building. This particular presentation relates to looking at traditional buildings and materials in the tropical rainforest area of southwest China. Originally, my colleague, Dr. Ring Gao, was going to make this presentation, but unfortunately, earlier this week, she was taken ill. And because I was involved with the project, I've stepped in. So I'll begin to talk a little bit more about the project. Actually, this particular presentation is part of a much larger and ongoing piece of work linked to a research network which we are running in southwest China. It's actually sustainable and creative villages, the focus being on villages. Now, you might wonder why we would choose southwest China and why we would choose villages. First of all, southwest China is some distance away from the more normal areas on the east coast that's linking Beijing, Shanghai, Guangzhou, Hong Kong in China. And secondly, it's an area which is populated by many different ethnic groups. Although 93% of the population in China are Han ethnicity, in the southwest areas, you get a particular predominance of some of the other 50 or so different groups. So it makes a particular interesting area to look at. For this paper, we are thinking in particular about how to achieve comfort in what we might think of as moderate to extreme climate that is experienced in southwest China, in an area known as Xishuangbanna. If you were to look at a map, which we will do shortly, you will find Xishuangbanna is in the far southwest corner of China and has some particular climatic variations, which range from a tropical area to one, because of its high elevation on the plateau, actually has a more pleasant climate because of the elevation. The region of Xishuangbanna is about 20,000 square kilometers, has a long and interesting history, often linked to some of the other countries in that area. And also because of its lowland tropical rainforest, presents a particular area of interest and need of research. There are dry and rainy seasons, but the main wet season, where 80% of the rain occurs, is between May and October. And it's only two places in China which are considered to have a tropical climate. It also has a very high biological diversity, and at the moment there has been a United Nations summit looking at biodiversity in the province as a whole. So looking at the particular area, the area that's of interest is in the southwest corner, near to Burma or Myanmar and Laos. The provincial capital of Yunnan, which is in this area, is Kunming, but actually the area of interest is much closer to the border, and one of those areas which inserts a little bit into Laos. And it's an area which is populated generally by a particular group called the Dai, who have links with other groups in that area. The Dai ethnic group in Yunnan province, as it borders Myanmar and Laos, its capital is Jinghong, and it's located on the Mekong River, or as it's known in Chinese, Lancang River. Now, the photo you can see there is of the traditional bamboo and timber buildings that would be associated with that particular ethnic group, the Dai ethnic group. And it evolved to accommodate the wet and hot climate, so plenty of room for ventilation beneath, and plenty of opportunity to engage with natural ventilation higher up by removing some of those panels that you can see there. A very interesting area to visit, and I've had the pleasure of going there for approximately the last 10 years. Now, the region itself is well known for its production of tea. However, since 1955, other vegetation has been introduced, particularly rubber and to some extent banana trees, planted in the area and creating a difference in the sort of biodiverse nature of the place. And this was enhanced by the fact that rubber prices increased during the 1990s, encouraging the planting of different types of crops. And this in turn had a knock-on effect on the types of materials available for construction. And this has caused a difference in the way in which the local population react. It should also be said that in rural China, and particularly southwest China, the national government policies have encouraged a lot of revitalization of villages to try and bring them up to the same kind of economic and social standards experienced in other parts of the country. And this has led to something of a, I wouldn't say a building boom, but a building transformation, which has meant that some of the traditional forms of design have been less favored and being replaced by some of the alternatives, which can be constructed more quickly so as to replace, and which have for some of the facilities and amenities that many people would like in a modern house. So compared to an old property, perhaps with no inside toilet or bathroom, the newer properties would have those kinds of amenities. And this has caused a quite significant shift in the way the villages appear and the way in which they operate. And you can see a couple of extra bits of information. They're talking about the way in which biodiversity loss has led to reduced water availability, pollution, soil hardening, and so on, which has meant some limitation on the kinds of construction techniques that could be used. This diagram here shows a typical layout at the ground floor and first floor of a Dai ethnic house, and also a section through the building. We've studied a number of these kinds of buildings to get a good understanding of how traditional construction operated. But what you can see on the lower level, which is the ground floor, of a large open space, which is traditionally used for storage, for work activities, craft activities. Indeed, for a garage, you can see a motorbike included on the plan on the left. And the main occupied area being on the first floor with steps up to it, allowing the first floor to benefit from increased natural ventilation, yet providing some shelter for the ground floor. And one of the changes that's taken place has been to have a much greater use of that ground floor for carrying out other activities. So the traditional form of the building has been more morphed or changed into a new kind of design in order to accommodate both the changed availability of materials, but also the changing ways in which people use buildings and their changing priorities. One of the ways that this is most reflected and is very quickly obvious if you visit the area is in the change of construction materials. The old traditional Dai buildings were elevated on the ground floor and evolved to meet the more wet and hot climate areas where flooding was quite common. But in more recent years, because of the way in which the precautions have been taken to avoid flooding and because of the changes in emphasis in the way buildings should operate, they've changed in the way in which the buildings evolved over a number of generations to cope with the weather. And since about the 1980s, the Dai houses in China and Thai houses in other Southeast Asian countries have been changing quite quickly. One of the reasons is these changing materials. So you'll find some of these things evident in Thailand, Myanmar, Laos, and also some of the other countries around that. Moving to a rather more lightweight construction in some of those countries using corrugated metal sheets, corrugated fiber cement tiles, cement boards, gypsum plaster boards, precast and cast in place concrete and plywood. However, in the Chinese side of the border, in particular in Sichuan, you find that we're building more in concrete block or brick. And these have been rapidly replacing the traditional timber buildings that were raised above the ground. So quite a significant variation in the appearance from what was there before, including things like steel roof structures, concrete roof tiles, terracotta floor tiles, really moving into quite a new area. And this has had some knock-on effects because the people who occupy those zones are not very familiar with those kinds of materials or how they can be used to maximize or optimize the internal conditions. Also, with improvement of road and drainage systems, ground floors are being increasingly used as living spaces. So you're finding the main occupied space is no longer raised up and able to benefit from normal natural ventilation. We find increasing use of large windows, usually glazed on all 4 levels, and changes in the internal light, but also in changes in terms of heat gain from the sun. Some natural ventilation is found, but the concrete and big brick structures may have some difficulties or some changes that need to be optimized. And one of the biggest drawbacks is basically the traditional professional builders no longer have the facility to understand how best to optimize using these new materials. They don't have the skills or the knowledge. And if I show this image of more modern buildings from the 1980s and up to the 2020s, you can see how the design is quite significantly different to the traditional timber construction. Still some of the original features, particularly in terms of the roof shape and the roof angles, but entirely different in terms of the fact that the building comes down to ground floor and also has different kinds of openings, usually glazed, and different kinds of materials, leading to the issues I've previously described. So these new buildings can carry some of the traditional characteristics, but mainly are evidencing the contemporary characteristics of construction materials. And these are constructed almost entirely on the same family plots, but instead of perhaps not exploiting the full area, they are often right to the edge of the plot, fully occupying it, reducing the availability for natural ventilation and so on. Following the same orientations indeed, which means that sometimes the optimization that can be gained by changing orientation is not being taken. We did a few basic experiments to look at the temperatures in in the traditional houses, which were generally offering a few degrees benefit in diurnal range of temperature. There are some opportunities, however, with these new materials to increase more of the thermal lag, more of the thermal mass, which could be beneficial in more modern designs. So we began a process of looking at, I think it was about 15 different locations, and we used the climate consultant software because it was a simple and relatively straightforward visual way of conveying information to see what the differences might be. Clearly, the local population and the local builders were not as aware as they ought to have been of some of the new opportunities that could come if you built from new materials and built with a new purpose to be more climate sensitive. But we can pick out some of the key features here. And one of the things that we were quite interested to do was to look at the changes in the amount of comfort hours that might be accrued from moving from a traditional calculation technique of the basic building based on PMV analysis, where we added in the potential for use of adaptive approaches. And this had been a substantial increase in the passive measures that could be used to create more comfortable environments, which was really quite a useful benefit to look at. There's a lot more information I could convey here, but at the moment, I just ask you to accept this as an example of it. We actually then carried out a much more
only
detailed...
3 minutes left.
That's fine. We then carried out a much more detailed analysis using Energy Plus. One of the areas where we think we could re-emphasize and rebuild some of the better ways of creating buildings is to use an enhanced craftsmanship. So training people who are local to the village to understand the new skills and new techniques that they need to try and resolve some of the conflicts between promoting environmental protection and economic development, because at the moment, most locals just really want to get to a situation where they have a new house with all the modern amenities, but don't really think very carefully about the environmental impact, either internal to the building in terms of comfort or external to the building in terms of climate change or impacts on other pollution areas. So we were quite pleased in some of the more recent visits to see local government and planning departments starting to issue guidance documents, but there is still some way to go. We've tried in our project to develop more beneficial beneficial guidance documents, and also to hold a number of seminars and symposia to help develop the understanding in the local population and also in the local professionals. So we think that there are more policies needed in order to optimize the outcomes that we're aiming for. Yeah. So in summary, I would say that The paper is really arguing that appropriate sustainable methods and assessment indicators can be devised and used, but need to take account of the local knowledge or the lack of local knowledge that there is at the moment in order to develop the optimum solutions. And these should be suited to the local climate and supported through the education system, through local craftsmen and so on, to evolve to perhaps have traditional apprentices that can use these new techniques. And we think there's a really significant opportunity given the large population and the still very large number of villages in China to make a real difference. Although we've seen, even from an international perspective, large movement in people in China from villages, from the rural areas to the cities, we still find a very large number of people living in villages, living in rural communities, and therefore there's still a big opportunity here that we could make use of. I will stop there and say thank you very much for listening.
Thank you very much, Professor Adrian, for your interesting and informative presentation comparing traditional materials and traditional buildings in terms of thermal comfort. And also, I would like to thank the first two presenters, Dr. Hacker and Dr. Nikita. Now the floor is open for questions. I guess I have only one question posted early by Professor Adrian. This question is for Dr. Hacker. So I would like to ask if you will be producing a simplified design guide based on your work to aid designers and developers to optimize the design. So, Dr. Hacker, if you can answer the question,
sure.
Please.
So right now that, as the presentation has told, that it is done for warm and humid climate. So now the next step for our research is to take consideration into each and every climate, major climate, according to the National Building Code in India, and go for a study for those climates, and then at the end to develop a tool which optimizes the cost, environment, energy consumption, and environmental aspects altogether.
Okay, thank you. Any other question from the audience? If you can post it, or you can speak out if you want. I'm not, of course, very familiar with the topic, but I have just a general question. We know that double wall is much better performing in terms of thermal insulation compared to a single wall. Quite similarly, you're talking about the double skin facade and single skin facade. So what is quite new here? What is the contribution here you're bringing out?
Okay. So in terms of like double skin walls, like cavity walls and all are better for installations. But in terms of India, this technology is firstly not being used in many places. And other than that, if you have seen the building, the second skin was not fully, it was perforated in nature. So if you get to a cavity wall, like if you talk about a cavity wall, there is no ventilation, and that a buffer will act great. But in terms of double skin, you can actually walk in that buffer zone, and you can do other activities in that buffer zones also. And other than that, in terms of various climate, in terms of warm and humid, in terms of totally hot, but there is no humidity. So things vary according to the material that is being used and the cost that is being employed on. So to check for that, these studies were being done. So a basic guideline can be developed. We can directly use this in construction and all.
Okay, thank you. We have, I think, another question. This will be later on. So this is for Professor Adrian, I think. So
yes, thanks, Sue. Thanks, Sue, for the question.
Dr. Adrian, can we just leave the question a bit later on?
Yes, no, that's fine. That's fine.
Yeah. Sorry for that. I would like just to know if there is any question for the second presenter, Dr. Nikita. If we don't have any questions, so I have just a general question. You're comparing lime plaster with the cement plaster. Well, myself, I'm a specialist in materials, so I know very well that the thermal conductivity of lime is lower than the thermal conductivity of cement. So of course, the insulation properties of lime plaster is much better than the insulation properties of cement plaster. So what is the new thing that you're discussing here? If you can develop a little bit more.
Yes, sir. So just to have explain you a bit more about it, as we know about the thermal properties of lime, what new I am adding to it is the moisture buffering capacity of lime. As we are talking more about thermal and human comfort, it's not just now restricted to only temperatures. We are taking into account humidity as well. So as when we approach to warm and humid climates, as the humidity levels are very high, going towards like materials which are non-porous or have less moisture buffering capacity, instead we can use or employ lime to buffer that moisture and reduce the latent load. So similar studies have also been researched where they have done a post-occupancy analysis to understand in a warm humid climate how lime is proving beneficial. So my study was to understand how the coupled effect, both as the moisture buffering capacity and as well as thermal property of lime, is proving to be beneficial as compared to cement.
Okay, thank you, Dr. Nikita. But I have just a comment on that. Lime is causing too many problems in terms of durability.
In durability.
Especially in a humid area.
Okay. But so just to have a more insight on this, durability as in wear and cracks you're talking about?
Yes, I'm talking about durability, of course, yes.
Yes.
I know maybe it's out of your study, but connected to of course, what you were discussing in your presentation. Of course, in terms of thermal insulation, is providing a much better performance than cement plastering. But of course, in terms of durability of the material, lime is always causing too many problems in terms of durability. So it is a weak material, especially when it is in contact with some harmful chemical agent like acids or sulfate. Or, so this is just a comment. It's not really a question.
Okay.
If there is any question to Dr. Nikita, so we can move to...
Dr. Muhammad, I have a question.
Yes, please, Dr. Badr.
Since she mentioned here an energy consumption of 35%, just can you just a little bit explain what's the 35% of energy consumption here? What do you mean by this?
So it's the annual consumption, 35% as to the energy consumption, or talking about the global scenario of India. How much India accounts for the total energy share.
Okay. So that's mean this is your Indian standard.
Yes, yes.
Okay. Thank you.
Thank you, sir.
Any other question? So we can move to the third question. So that was asked for Professor Adrian. So Professor Adrian, you can just...
Yes. Okay. Thank you very much. I would like to congratulate the two other presenters because I thought the technical detail was very interesting. I will try and answer the question from Professor Ruff. I think resilience is not something which is just technical or materials orientated. I think resilience is something that comes from social, economic, and people as well. And one of the key things we've noticed in the work in China is that if the local population, particularly if the local committees, the people who run villages understand, then the outcome is much improved because they make modifications, they improve things for themselves rather than having a technology imposed on them that they don't understand. So I would say resilience actually comes more from people than from the materials. But certainly it's a case of if the local people can make a choice, which is based on knowledge rather than something which comes from outside, then we get a more successful outcome.
Any other question?
I can see that, I think Sue's asking if the roof form is critical.
Yes, yes.
Not really. There isn't a big difference, and indeed the shape and appearance of the more modern roof is designed to look very similar to the old one. I would say the main variation is in the openness of the walls for ventilation and the use of glazing, which obviously changes the visual impacts and heat gain and heat losses from the building.
Yeah, again, just I have a general comment. Since we are talking about traditional buildings and traditional materials, so as we know also traditional building materials, usually they have also very good insulation properties. But the issue is always the mechanical and durability properties. So how you can make a balance between the two performances?
Yeah, if you're asking me, I think that is a tricky area, because we've also been doing studies, for instance, in Vietnam, of applying passive house techniques in the hot, humid climate. And you can see that the actual techniques of construction have a really important role to play. And I think I would come back to one of the final slides that I had, which is we do need to make sure the people who are designing and also, very importantly, installing or constructing the buildings understand how to do it correctly. Then we're likely, if we are introducing some new materials, the insulation in different places, we're more likely to get a successful outcome than if the people don't understand. As I suppose I bring it back to, it's a non-technical issue, because you have to understand it in order to do it correctly. That's sort of how I would try and interpret it.
Thank you, Professor Adrian. So with that, I think if you have any other question from the audience, otherwise we can close the session. I guess there is no more questions. So I would like to thank all of you, the presenters, Dr. Hacker and Dr. Nikita and Professor Adrian, for your very interesting presentations. And also I would like to thank the audience for your contribution in this session. And I wish you a nice weather evening, or a nice night, or nice day. So thank you so much for all you presenters and audience, and see you maybe in next session tomorrow. Thank you so much. Thank you for everyone.
Thank you.